Good morning. This course is on machining process and the topic of influence of machining parameters in determining the machining time. So the earlier classes we have seen that the construction of different engine lathe, which has an headstock with giving it power, and the chuck will have an holding the workpiece, and the tool and the cross slide will help you to move the tools, and other carriage and base and bed will support it, and also the tailstock will support the workpiece also. So the different kinds of lathes are available. One is there can be a watchmaker's lathe, which can be the smallest one, and it can be able to do and machining on a very tiny parts. And the engine lathes will be available in our machine shop, and the turret also available in our machine shop, where the turret lathe will have a multiple tools will be held in a turret, and indexing this one able to do a multiple process. And the size of the lathe is decided based on the size of the workpiece. Here you can see that the larger work part has been held in a very large lathe. You can see that it's a very huge lathe which are used to machine a crankshaft for a very large uh, engine. And you can see that here very carriage wheel itself has a carrier to move the tools, and a worker may stand in this and able to do it. So the inference is the size of the workpiece will decide the size of the machine tool we are going to use it. So the recent trend is going to be on the CNC lathe will be available, and which is going to be completely computer controlled, and try to load our coding and able to machine in better fashion than that of a conventional machines. So in general, the inputs will be of the machine tool, and you require a cutting tool, and the workpiece has to be operated in a proper setting, and with the support of work holding we are going to ensure this cutting process. So the machine tools may be decided based on the size and shape of our work part, and the cutting tool will be the required operation to be performed on the work part, and which has and the nomenclature, material, and the hardness, even the finish and the coating it has to withstand at high forces sometime. And similarly the work pieces has to be with a material property, and its nature will decide which will affect on the machining process. So the machining process may be in a single point cutting or multi-edge uh, tool cutting maybe, and in case of lathe is concerned, it's a single point cutting tool uh, with the support of with the support of the cutting parameters has been properly set with the depth of cut, speed and feed, and also the working environment with the use of a coolant or lubricant, and oxygen and temperature effect may be considered during the operation. And this process will be supported with the work holders. It may be a fixer, jigs and chucks with the nature of the work part is concerned. So this will be reflected in terms of through the measurements, the cutting forces, the dimensions, and the surface finish, and the tool wear, and the deflection temperature can be measured, through which we can able to predict out what is the amount of the power is required, and the derived quantities such as the stress levels we can able to predict it from this measurement. So the so many parameters will be involved in machining, and in particular the cutting parameters will play a major role here in the determination of machining time and the metal removal rate. So the last classes we have seen that the effect of the cutting speed on the forces, and each one these three parameters are the major one which will be influencing all the variations in the forces involved. Henceforth is going to be the stresses, and thereby we will be able to decide what is the power required for this machining process. And during this process we may come across with the different types of chips types. It may be an discontinuous, continuous, or continuous with build-up edges. This is based on the nature of the work part and the cutting parameters is concerned. In order to overcome this continuous chip, we may use a chip breaker to handle the chip in a proper form. So the irregular machining will be resulted with the surfaces like this, and which is maybe a resultant of the vibrational resonance of the entire machine system or the workpiece cutter alone, which causes a poor surface finish and fast tool wear, and noise may be affected. This will be a major influencing factors will be the stiffness of the workpiece, how it has been held, and what is the nature of a cutter is going to be, and the machine cutting parameters such as speed, feed, and depth of cut. Sometimes the cutter geometry may also plays a major role in these, like our rake angle and clearance angle. That is improper selection of angles, or sometimes tool wear. The solution will be we are supposed to control over the cutting parameters, especially the speed, and you are supposed to increase the stiffness to have an effective quality machining to enable. So the cutting geometry as well as the shape of the uh, contact point plays a major role. As we see here is kind where as we move from the very sharp end to our blended, we may have a higher strength, but the sharp end is required for making machining, and very sharp in the sense the cross section will the minimum will affect into your a greater chip breaking. So we will have an this kind of shapes will be utilized as a insert sometimes based on the nature of the metals tool workpiece material is concerned. So indirectly these all the things will affect on the total cost of during the machining. So on the changes on the speed or any cutting parameters will have an influence on the total cost of the component itself. So today this video will present that to know that what are the process parameters will be involved in during this machining. So the spindle speed, and another thing is going to be your the feed and the depth of cut will be the major component, which will be mutually perpendicular to each other. So cutting velocity always expressed as a meters per second, and it's important to use a correct speed for a given material to get a desired surface finish. If you are selecting very too high, the cutting tool breaks down rapidly. If it is selecting a too low, it's a time loss, low production rate, hence the cost of production keeps on increasing. So that requires a proper selection of cutting speed of the material, and the diameter of the work must be known to for this. So proper spindle setting will be simply a division or ratios between the cutting velocity in terms of meter per minute with the circumference of a work part. And this photo represents that different cutting conditions in respect to this is concerned. It's going to be variation of cutting velocity and how it has been influenced. So higher the speed, you get a better finish, and lower cutting speed will have a rough cutting will be, and the rough surfaces you may end up. So as the speed increases, surface finish increases. The next component is going to be a feed, and the distance of the cutting tool advances along the length of workpiece for every revolution of the spindle. Feed of the lathe depend on the speed of the lead screw or the feed screw it has, and the speed of the feed rod controlled by the changing the gears, the quick change gearbox available in the machine tool. And feed will be a simple representation. Here is a direction along this way the length of cut or length of the workpiece for a turning process is concerned. So the feed is the distance of the tool distance the tool advances for every rotation of the work part. So here we have two terminology, that is a feed and a feed rate. Feed as I said is can be represented in terms of mm per revolution. Sometimes the same thing can be represented in terms of mm per second. Is another way of representing the feed. So this is the expression for the feed rate, that is a feed with respect to the rate of the spindle speed has been set. And this has a great influence in surface finish. That is a ultimate aim of this machining is concerned. So this is an empirical relation that the effect of feed as well as the nose radius of the cutting. cutter or a cutting tool is concerned. So this will be a major parameters that will be influencing the surface roughness. Hence, the feed supposed to be properly controlled for getting a better surface finish. So we have two kinds of cutting conditions. That is a rough and finish cut. That is roughing cut is going to be a which is required for excessive material to be removed off quickly. For initial cuts with a higher depth of feed rate, that is a coarse feed will be at 0.25 to 0.4 mm will be desirable, and the finishing cut it has to bring the diameter to size, produces a good surface finish with a 0.07 to 0.01812. So this represents the effect of feed in terms of the changing in the feed values. So as you have the lower the feed, surface finish will be better in this aspect. So the nature of material and the kind of cuts will decides the selection of an appropriate feed for machining is there. So a proper combination of tool material and workpiece material with the kind of cuts will decide the appropriate feed for this one to get a better surface finish. So the next parameter is going to be depth of cut. Distance of tool penetrates into the workpiece. It is equal to the half of the differences between the initial diameter and the final diameter. And in general, that will be one roughing, one finishing is going to be considered. Then the roughing will have a very larger depth of cut, and the finishing will have a very minimum depth of cut. So this is the arrangement in which the side view of this cutting, where is this is going to be a machined diameter and it's going to be a parent diameter. The difference between these two, difference between two and half of it will be the depth of cut. So that has been defined here. The D1 will be the parent material diameter and D2 will be the machine diameter. The depth of cut will be the half of this difference. So this is going to be an effect of depth of cut is concerned. Is going to be as the depth varies, the surface finish disturbs. So in this case, as a lower the depth you have, and better the surface finish is possible. And proper control over this with three parameters will have an effective mistake. So these parameters will be influencing on the machining time, and hence the machining time will be indirectly decides your production rate, hence the cost involved. This is a simple example to show that the rough cutting and other things you can see here, and this will be discussed in the next class, tutorial class, and this will be ends with a total machining time of 29.1. So next observable output quantity is going to be a metal removal rate, which is going to be the volume of metal removed during one revolution. So this will has an influence of the depth of cut and the feed and the diametrical movement. So this will decides in this case. If you are able to represent the same MRR, in this case can be thousands into thousands is going to be meant for work conversion of mm to meter or meter to mm. Since the velocity has been given in terms of meter per minute, this has been given as 1000. So based on the unit consistency, we are supposed to do it in a proper form. So hence the MRR will be influenced by all three factors, that is V, F and D. V is for our cutting velocity, F is for feed, and D represents the depth of cut. Hence the control over these three things will have an effective quality machining. So these are these references, and you can go through this web links to understand this one in a better form. Thank you, and meet you again.